Okay, so for number 1, they're asking you for the limit as x approaches 3 of 21. Now remember, anytime that you have a constant, your limit is always going to be just that constant. So then your final answer is just going to be 21. All right, for number 2, there's a couple ways that you can look at this. We're looking at the limit of 5 over x as x approaches infinity here. So infinity, obviously, the number is getting larger. X would be getting larger. So for example, what we could do is we could try plugging in numbers. So 5 over 1. Okay, then let's try 5 over 2. And then let's try 5 over 3. And let's try 5 over 4. And so on and so on and so on. And so then if you look at that, you'll notice that these numbers here are getting smaller and smaller and smaller the further to the right we go. So then we can safely say then this limit as x approaches infinity would be 0. And that's your answer. Now the other way to look at that is you should know that 5 over x resembles the graph 1 over x. And the graph of 1 over x looks like this. Remember, you should have that memorized. So if you look at this graph then, as we go toward infinity, so we're going to follow this graph as we go toward infinity, we get further to the right. Notice that this graph is getting lower and lower and lower to the x-axis, therefore approaching 0. Okay, number 3 is almost identical to number 2, except that we have an x squared on the bottom. So again, we can start by just doing 6 over 1 squared, then we could try 6 over 2 squared, and then 6 over 3 squared, and so on and so on. Okay, you can see that the denominator of these fractions will get larger, but if it's a fraction and the denominator is getting larger, the actual value of the fraction will be getting smaller. So then it would be safe to say then this limit is going to equal 0. Okay, now the other way again we can look at it is 6 over x squared resembles the graph 1 over x squared. And again, that should be memorized. But let's look at the graph. There's the graph 1 over x squared. So if you look at 1 over x squared, as we go toward infinity, this value, this graph here, is getting closer and closer to 0. All right, so when we look at this one, that's x squared minus 64, by the way, which you should have on your ditto. Just didn't type out too well. I see that in the numerator there, that's the difference of 2 perfect squares. So I'm going to go x minus 8. X plus 8, and then in the denominator I have x plus 8, and then I see that I can then cross out a common factor on the top and the bottom. Okay, I'm just going to transfer this down here. So then I have the limit as x approaches 8, technically, of just x minus 8. And when I plug that 8, this 8 here, right in here, I'm going to end up with 0. For this question, I would start by trying to plug in the 5, but when I plug in 5 into this expression here, I end up getting the absolute value of 0, which is 0, over 5 minus 5, which is also 0. Remember, that's an indeterminate, and we can't have that. So what I would probably suggest that you do, since 5 is the number that tends to be giving you that indeterminate value, I'm going to try plugging in numbers into the original expression that I circled in red, and I'm going to try to plug in numbers lower than 5 and some that are higher than 5. So for example, let's say I plug in x equals 2. So if I plug in x equals 2, I'm going to get the absolute value of 2 minus 5 over 2 minus 5. Okay, so that's going to be negative 3, but remember that's an absolute value, and over negative 3. So that's going to be 3 over negative 3, which is going to be negative 1. Okay, I could try plugging in something a little bit closer to 5, let's say like 4. Okay. So I'm going to do 4 minus 5 in absolute value, and then 4 minus 5 not in absolute value. that's going to give me negative 1 in absolute value over negative 1 not in absolute value. So that's 1 over negative 1, and that's going to give me negative 1. Now, you can try other numbers. I'm not going to do them all, but you can try other numbers that are lower than 5. Plug them in, and you'll see you'll constantly get a negative 1. Okay? Now, likewise, then, what I'm going to do is I'm going to plug in something bigger than 5. Let's say 6. So if I plug in 6 here, I'm going to get 6 minus 5 in absolute value, and then 6 minus 5 out of absolute value, which is 1 over 1, which is 1. Now, if you plugged in 7, or you plugged in 8, or you plugged in 9 into the original expression, you'll get the same thing. You'll get a positive 1 each time. So then basically what you have is a piecewise function. So then what's going to happen here is, let's just say this is an x value of 5. So then anything to the left of 5, the graph is going to be at negative 1. So kind of like here, I'm just going to go over that 5, sorry. Let's pretend that this value right here is negative 1 on the y-axis. Okay, and anything bigger than 5, in this case like x equals 6, will be at a positive 1 on the y-axis. So that's what your graph is going to look like. So then if you look at when x equals 5, look at what happens here. We have a big gap or a big jump discontinuity. So if that's the case, then the limit as x approaches 5 does not exist, and that would be your answer. All right, so for number 6, this is as x approaches infinity. So remember, when we have x approaches infinity, what we can do is we can do end behavior, which is taking the highest power on the top and then the highest power on the bottom, and simply just reducing those values. Okay, so I'm going to take this highest power here and this highest power here, and let's see what we get. So I'm going to get negative 6, and then I have x cubed over x cubed, which is going to cancel out. So therefore then the limit as x approaches infinity of this whole expression would just be negative 6. So for this question, if we try to plug in 0 into the numerator and the denominator, we're going to end up with an indeterminate again. So if you recall, we have done questions like this, and what we're going to try to do here is we're simply just going to try to get a common denominator of the numerator there. All right, so I see 3 plus x and a 3, so then I am going to take this denominator and multiply by 3, and I'm going to take this denominator and multiply by 3 plus x. Okay, now remember what you do to the bottom, you need to do to the top. So 3 plus x is going here as well, and 3 is going here as well. Okay, so then I'm going to have the limit as x approaches 0, and we're going to get 3 minus, and then I have 3 plus x, and over the new common denominator, which is going to be 3 parentheses 3 plus x. Now, please keep in mind that what I just wrote in red, okay, which is this right here, is technically being divided by x. Well, if I divide something by x, that's the same thing as multiplying by its reciprocal. So I'm going to just bring that down instead. Okay? All right. So let's see if we can just take this numerator. We're going to distribute this negative through, and let's just kind of simplify. All right. So I have the limit as x approaches 0. Okay, so let's distribute through here. So if we have this negative goes through to this 3, so that's going to be 3 minus 3, which will cancel out, and that negative will make this x negative, right? Okay, so then what I am going to end up with is negative x, right, over 3 times 3 plus x, and that's going to be multiplied by 1 over x. All right, well, that's a common factor, so we can cross those out. I'm not canceling out the negative, though. Okay, and then when I do that, I'm just going to go in this direction now because I'm running out of room. I'm going to have the limit as x approaches 0 of negative 1 over 3 times 3 plus x. And now I can simply plug in my 0. So I'm just going to take my 0 value here, plug it in here, and simplify that fraction. Okay? And oops, when I do that, I am going to end up with negative 1/9. All right, well, we have another end behavior, and we know that because it's as x approaches infinity. So I'm going to take the highest power on the top and the highest power on the bottom, and I am just going to simplify that. Okay, so that ends up being, well, the x squareds are going to cancel out. We've got 15 over 10, which when we reduce that is 3 over 2. Easy peasy. Okay, so we've done a bunch of these in class, and remember that when we do have a radical in the denominator, it's not rational, so we want to get rid of that. So all we're going to do is we are going to multiply by the conjugate. So we're going to multiply by radical x plus 2, both top and bottom, numerator and denominator. Okay, now don't go crazy. We do not want to distribute through that numerator, right? We just want to leave that. So we're going to write x minus 4, and we're going to multiply that by radical x plus 2, just leave that. And now, what we really have down here in the denominator is the difference of two perfect squares. So remember, then we can just kind of cheat and multiply the two first terms and then the two last terms. Okay, so radical x times radical x is just x, and a negative 2 times a positive 2 would be minus 4. Thus why we don't want to distribute through the numerator, because now we can see that we have a common factor in the denominator and the numerator, and we can go ahead and we can cancel those. So I'm going to cancel that out, and I'm going to cancel that out. All right, and then last but not least, all we're going to do is we're going to take this value of 4, and we're going to plug it right in there, and we are going to evaluate that. So that ends up being 4. For number 10, we are going to factor. If you look at that numerator there, okay, we can factor that numerator, and that factors to x plus 3 and x plus 2. And then in the denominator, we have x plus 2. And then I see that I have a common factor in the numerator and the denominator, so I'm going to cancel that out. And then all I need to do is plug in my 2 into what's left over. So I technically have the limit as x approaches 2 of x plus 3. So that will end up giving me 5. Number 11 is very similar to number 10. So we're going to start by factoring that. Numerator, when I factor that, is going to be x minus 2 and x minus 1. The denominator is the difference of two perfect squares. Oops, let's make that look like a 1. And then we can see that we have a common factor right there. Okay, so we're going to cancel those guys out. And then all we're going to do at this point is we're going to take this 1 and we're going to plug it into the denominator, and we're going to plug it into the numerator to evaluate that. So when I plug it into the numerator, I end up getting negative 1. When I plug it into the denominator, I end up getting 2. All right, so a little bit of a change of pace on number 12. We're going to first take a look at what we are approaching here. We're approaching pi over 3. So let's just kind of remember that pi over 3 is really the equivalent of 60 degrees. Okay, so what we can do here is we can, essentially what this is asking, whoops, let's just go like that. It's asking for the sine of 60 degrees, and then what we want to do is square that quantity. Okay, so remember what the sine of 60 degrees is. The sine of 60 degrees is radical 3 over 2. Oh boy, sorry about that messiness there. And we're going to square that value. So if we square radical 3, we get 3. And if we square 2, we get 4. There we go. So we're going to kind of take the same approach on number 13 as we did with number 12. So let's look at pi over 6 first. Pi over 6 is equivalent to 30 degrees. So what this is talking about is the secant of 30 degrees. Well, off the top of my head, well, or maybe your head, you wouldn't know what the secant of 30 degrees is. But remember, it's reciprocal trig function. The reciprocal trig function of secant is cosine. Okay, so we should know what the cosine of 30 degrees is. That's radical 3 over 2. So now if the cosine of 30 is radical 3 over 2, then the secant of 30 would be its reciprocal because they're reciprocal trig functions. So that's going to be 2 over radical 3. Now we can't leave that like that because we have to rationalize the denominator. So what I'm going to do is I'm going to multiply, remember, numerator and denominator. Okay. And we are going to get 2 radical 3 over 3. Bing, done. So here we go again. Pi over 6, its degree equivalent is 30 degrees. So then this is saying, let's plug in 30 degrees there, and let's plug in 30 degrees there as well. Okay? All right, well, the cosine of 30 is radical 3 over 2. And the tangent of 30 is radical 3 over 3. So that ends up being 3 over 6, which is a half. All right, so we don't need to freak out about this one too much here. We are going to be plugging in 0, right? Because it says right here to plug in 0. So we're going to plug in 0 here, and we're going to plug in 0 there. All right, so then when we do that, we're going to end up with the limit as x approaches 0 of e to the, now let's plug in 0. When you plug in 0 into that entire exponent there, that's just 0, right? What's anything to the 0 power? Think about that. Anything to the 0 power is 1, isn't it? Okay, so e to the 0 power, anything to the 0 power would be 1. So we have the limit of a constant. So that will just be the constant. So we're trying to determine whether or not this function is continuous. So if something is continuous, all you need to do is, let's look at our domain here, and do you see that it centers around the number x equals 3? It's not included down here, but it is up here. And remember, we talked about that really the equal to doesn't need to be here. It needs to be in one of these two spots. Okay, so what we're going to do is we're just going to start by, if you recall, we're just going to plug in 3 into both parts of the piecewise function. So if I plug in 3 into this top part here, I'm going to get the square root of 4, and the square root of 4 is 2. Okay, now if I plug in 3 into the bottom part of the piecewise function right there, I'm also going to get 2. So if you have the same values on the top and the bottom, then we can say that the function is continuous. So we're going to use the same exact method that we did on number 16 for this question as well. So we check out the domain. We're kind of centering around x equals 1. So we're going to plug in 1 into the top part of the piecewise function. And when we do that, I get 1. And we're going to plug 1 into the bottom part of the piecewise function. And when I do that, I get 1. So again, when we get the same thing on the top and the bottom, we can say that that function is continuous. Okay, so third time's a charm. This time we're centering around 2. So let's plug in 2 into the top, and I'm going to get negative 4. And when I plug 2 into the bottom, I actually get negative 3. Uh-oh! So that means that the function is discontinuous. Now, you could draw a picture by plugging in numbers, okay, and see what the picture looks like. You can also see here, because we are skipping from one number to the other, to a completely different number, we would then say that that discontinuity is a jump discontinuity. Okay, so 19 and 20 are giving you a little bit different of a spin on the questions from 17, 18, and also number 16. They're wanting you to assume that this function will be continuous, and they want you to find out what a is equal to. So I'm going to start by plugging in 2 into the numerator, and I get 4. And when I plug 2 into the denominator, oh, what am I saying? I'm so sorry. Hold the phone here. All right, let's go, drop back here. This is not x squared. This is x cubed, isn't it? So look on your worksheet. I made that mistake. So that should be x cubed. It looks a lot prettier on your worksheet there. So when I plug in 2, I'm actually not going to get 4 then. I'm going to get 8, aren't I? Okay. And now I'm going to plug 2 into the bottom, and I'm going to get 4a. Now they're saying that it is continuous. We are to assume that it is continuous. So we're going to set the top and the bottom equal to each other, right? Because we know if things are continuous, those should be equal to one another. And so then I'm going to end up with a equals 2. All right, so number 20, let's do it. We're going to plug in 3. And when I plug in 3 here, I'm going to get 8. And when I plug in 3 here, I'm going to get 6a. Again, they want you to assume that it's continuous. So then if it's continuous, we know those two values are equal to one another. And so therefore we know that a is going to be equal to 8 over 6, which we don't want to leave it that way. So that would be 4/3.